The amusement park ride, shown in Figure 10, is a large, rapidly spinning cylindrical room with a radius of 3 meters. Riders stand up against the wall, and the room starts to spin. Once the room is spinning sufficiently fast enough, riders stick to the wall. I really don't like the word sticking, but I see where they're going with this. Then the floor slowly lowers, but the riders do not slide down due to the friction of the wall. Assume the coefficient of friction between the wall and the riders is 0.4. Bump, bump, bump. And then the coefficient of friction is unitless. Okay, so draw an FBD. I prefer FBD because you're not really saying FBD, you're saying free body diagram. Never mind, it doesn't matter. It's one of those things on the internet that no one cares. Okay, draw a free body diagram of a person on the ride. What force or forces causes the net force on the rider? Calculate the minimum speed of the rider required to keep the person stuck to the wall when lowering the floor. Okay, so I'm going to draw a couple pictures here. So you got top view, you got your person. This thing is spinning, and the idea with a centripetal force, so you have, I think centrifugal is outward and centripetal is inward. It doesn't really matter. The idea here is that, that centripetal acceleration is v squared over r. It's a formula. And what that is telling you is that here is your velocity. Velocity is both a magnitude and a direction, because it's a vector. And so if you have the same magnitude, but now you're pointing this direction, the vector is changed. And that vector is changed not in magnitude, but direction. And the centripetal acceleration, what that tells you is, it tells you how much acceleration is needed to change the direction of the vector, of the velocity vector, without changing the magnitude. That's the whole concept of centripetal acceleration here. And so what's happening then is you feel an acceleration radially. So there's an acceleration, centripetal AC, is centripetal acceleration going inward. So the person naturally, just due to a body in motion, wants to go straight. But he's pressed up against this wall, and so the wall is then pushing him inward. So you're going to have, so the best way to probably say this then would be you have a centrifugal force going outward, force centrifugal, and then you have a force normal, basically due to the wall pushing you. And since the two forces cancel, you're not really moving radially inward or outward, even though you have a force radially outward and then a force radially inward. The net radial force, net radial acceleration is 0. Okay, so we have that, and that's the concept of what's going on here. And so if we draw another diagram, and more like this. This will be the wall. This will be the individual, very circular. And so I'm going to say this is force centripetal. This is force normal. Now, force normal is pressing against the wall, which causes a force friction, which based on, so we have the minimum speed required. So this is going to be minimum, meaning that the minimum force centripetal to create a force normal, which will then create a force of friction to just exactly balance out force of gravity. So this would be the free body diagram that I would draw, which actually would be the yes, that is the free body diagram I would draw. And what force or forces cause the net force? What force or forces causes the net force on the rider? So the question then asks, what's the net force? Well, even though I drew this force here, the centrifugal force is kind of referred to as a pseudo force, doesn't really exist. So the correct free body diagram, even though I drew it like this, would probably actually be like this without this force going outward. And you're like, well, wait a sec, this is crazy, this is unbalanced, and therefore this force normal is going to create an acceleration radially inward. Yes, that's a good feeling, But what's happening is this force normal is not creating a acceleration inward radially. This force normal is accelerating by changing the direction of the velocity vector. So all it's doing is changing the direction of the velocity vector. And if you have a change in velocity, you have an acceleration. So this would be the correct free body diagram without this force centripetal right here. Okay, so now for the second part, calculate the minimum speed of the rider required to keep the person stuck to the wall. Okay, so then we would do force centripetal. I know it doesn't actually exist, but it's convenient for this. Would be mass times acceleration. Acceleration centripetal is v squared over r. So v squared over r. That's going to be force, whoop, that is a terrible F. Force normal. And then we know that force friction equals, that's another terrible F. Force normal times coefficient of friction, we'll call it static because we'll assume it's not moving, which we know from up here is going to be mv squared over r times coefficient of friction. I think they told us it's point S. And that's going to exactly balance out, because we're told the minimum speed, mass times gravity. Take it one more step. Oh, no, still with blue, V squared equals gravity times radius over mu s, static coefficient of friction. Therefore, minimum velocity, I could do the min equals gravity times the radius over mu square rooted, which is, get out our calculator, on clear gravity, I'm going to say 9.81, we could say 9.8, probably even 10, times radius, which is, was it 3? I think it's 3, times 3 divided by coefficient of friction, which is 0.4. It actually makes the whole thing bigger. Second square root, second answer. And 8.58 meters per second, which seems pretty quick. 8.58 meters per second. Okay, so to backtrack what we did here, concept here is we have something spins. This spinning causes a force normal due to the pseudo-fictitious force centripetal. This acceleration inward is a centripetal acceleration, which is v squared over r. This is the acceleration required to change the direction of a velocity vector without changing its magnitude. That force normal, the force normal is pushing from the wall, it is going to create a friction force. Friction is force normal times coefficient of friction. And we then related that to gravity to kind of balance it out, so someone is essentially sticking to the wall, but really it's, I guess, frictioned to the wall. So that's how I'd approach this problem. Hope it helped. See you next time.